What if I told you that the instrument responsible for mapping 70% of our planet's surface was invented by accident? While sailors were literally dying, lost at sea with their expensive astrolabes, three men in three different countries simultaneously created the same device without ever meeting. This is the story of the Sextant, the navigation tool that dethroned a 2,000-year-old king and changed the course of human history forever. But here's the twist. The astrolabe wasn't actually bad. So why did it fail? If you're fascinated by how a simple piece of metal changed world exploration, smash that subscribe button and hit the like icon right now. Because what you're about to discover will completely change how you see maritime history. Let's dive in. Let me take you back to the year 1697. I'm standing on the deck of a British warship, HMS Association, and around me are 946 sailors who have no idea they're about to die. The commander, Admiral Sir Cloudesley Shovel, holds in his hands the most advanced navigation instrument of his time, a mariner's astrolabe. It's beautiful, made of brass, mathematically precise, and has been used successfully for nearly 2,000 years since the ancient Greeks perfected it. And yet, on October 22nd, 1697, this entire fleet crashes into the rocks of the Isles of Scilly off the southwestern tip of England. Almost everyone dies. Why? Because the astrolabe, for all its mathematical perfection, had a fatal flaw that nobody wanted to admit. You see, I grew up thinking the astrolabe was this perfect medieval instrument. In school, they showed us pictures of astronomers and navigators using these intricate brass discs covered in engravings, and we were told it was the pinnacle of ancient technology. And in many ways, it was. The astrolabe could measure the altitude of celestial bodies, tell time, determine latitude, and even predict the positions of stars and planets. It was essentially an analog computer from the medieval period. But here's what they didn't teach me. The astrolabe was nearly useless on a moving ship. Think about it. To use an astrolabe properly, I need to hold this heavy brass disc perfectly vertical, align its sighting arm called an alidade with a star or the sun, and then read the angle on the engraved scale. Now imagine trying to do that while standing on a wooden deck that's pitching and rolling in ocean waves. The ship moves forward, backward, left, right. The astrolabe swings on its suspension ring. My measurements become wildly inaccurate. I recently spoke with a maritime historian who told me something fascinating. Experienced navigators in the 16th and 17th centuries knew their astrolabe measurements could be off by 2, 3, sometimes 5 degrees. That doesn't sound like much until you realize that at the equator, 1 degree of latitude equals 60 nautical miles. A 3-degree error? That's 180 nautical miles, the distance from New York to Philadelphia. You could miss an entire island chain, sail past your destination, or like Admiral Shovel, crash into rocks you didn't know were there. But the problems didn't stop there. The astrolabe was also incredibly difficult to use in certain conditions. Try measuring the sun's altitude on a bright day without burning your eyes. Try reading the tiny engraved markings in the dark. Try keeping your hands steady in freezing Atlantic weather while wearing gloves. Try preventing corrosion on the brass mechanisms when you're constantly exposed to salt spray. And here's the thing that really gets me. Sailors knew all of this. Ship captains knew their instruments were inadequate, but the astrolabe had prestige. It had history. It had the weight of 2 millennia of astronomical tradition behind it. To suggest that it needed to be replaced was almost heretical. It would be like me standing up today and saying we need to replace GPS satellites with something better. People would look at me like I was crazy. Yet sailors were dying, ships were being lost, fortunes in cargo were disappearing into the ocean. The British Navy alone lost dozens of ships every year to navigation errors. The economic cost was staggering, but the human cost was even worse. Families lost fathers, sons, and brothers because the instruments we trusted couldn't handle the reality of ocean navigation. I want you to understand something crucial here. The astrolabe's failure wasn't about bad mathematics or poor craftsmanship. The mathematics was perfect. The craftsmanship was exquisite. The failure was about context. The astrolabe was designed for astronomers standing on solid ground, not for sailors on moving ships. It was a brilliant solution to the wrong problem. And this is where our story really begins. Because by the early 1700s, the maritime powers of Europe, Britain, France, the Netherlands, Spain, were in a crisis. They were racing to explore and colonize the world, but their navigators couldn't reliably determine where they were. The nation that could solve this problem would dominate global trade and become a superpower. The pressure was immense. The stakes couldn't be higher. What happened next is one of the most extraordinary coincidences in the history of science and technology. Imagine this scenario. 3 men in 3 different countries, none of them communicating with each other, all simultaneously invent essentially the same revolutionary instrument within months of each other. This isn't science fiction. This actually happened in 1731, and it's one of the most fascinating examples of what historians call simultaneous invention. Let me introduce you to the 3 protagonists of our story. First, there's John Hadley in England. I picture him in his workshop in London, probably covered in brass filings, obsessively grinding and polishing mirrors. Hadley wasn't a sailor. He was a mathematician and instrument maker, a fellow of the Royal Society, which was basically the most prestigious scientific organization in the world. He was methodical, precise, academic. When Hadley looked at the navigation problem, he saw it as a mathematical puzzle to be solved with optics and geometry. On May 13th, 1731, Hadley presented his invention to the Royal Society, a reflecting quadrant that used mirrors to measure angles. The room, full of scientists and gentlemen, was skeptical at first, but then Hadley demonstrated it. Unlike the astrolabe, his device could take accurate measurements even when moving. The key was the double reflection principle, but I'll explain that revolutionary concept in a moment. Now, while Hadley was impressing the Royal Society in London, across the Atlantic Ocean in Philadelphia, there was Thomas Godfrey. Godfrey's story is completely different. He was a glazier, a man who worked with glass for a living, and completely self-taught in mathematics and astronomy. Picture a working-class artisan, hands rough from manual labor, who studied advanced mathematics by candlelight after long days of work. Godfrey had been wrestling with the same navigation problem, and he came up with essentially the same solution as Hadley, a reflecting instrument that used mirrors. He called it a reflecting quadrant as well. The remarkable thing is that Godfrey developed his version independently, working from first principles, driven by conversations with sea captains who complained about the astrolabe's limitations. When Godfrey's invention was presented to the Royal Society later in 1731, a bitter priority dispute erupted. Who invented it first? Hadley had presented his version in May, but Godfrey claimed he had built his as early as 1730. Accusations flew. National pride was at stake. The British establishment rallied behind Hadley. The American colonists supported Godfrey. But wait, there's a third inventor. In France, a man named Pierre Leroy independently developed a similar reflecting instrument. The French called it an octant, but the principle was the same, using mirrors to measure angles between celestial bodies and the horizon. How is it possible that 3 men invented the same thing at the same time without communicating? I've thought about this a lot, and here's my theory. The problem had become so acute, the need so desperate, that the solution was almost inevitable. It's like how Darwin and Wallace independently developed the theory of evolution at the same time, or how calculus was invented by both Newton and Leibniz. When a problem reaches a certain critical point, and when the necessary technologies become available, multiple minds working independently can converge on the same solution. By 1731, several key factors had aligned. First, mirror-making technology had advanced enough to produce clear, flat, reflective surfaces. Second, the mathematical principles of optics and reflection were well understood thanks to scientists like Newton. Third, the economic and military pressure to solve the navigation problem had reached a breaking point. And fourth, there was a community of skilled instrument makers and mathematicians capable of turning theory into practice. What's particularly fascinating to me is how similar the three designs were. All three used a pivoting arm with a mirror, a fixed mirror, and a telescope for sighting. All three understood that by using double reflection, you could measure angles twice as large as the physical arc of the instrument. All three recognized that this design would be inherently more stable on a moving ship than the astrolabe. The priority dispute between Hadley and Godfrey was never fully resolved. Today, most history books give credit to Hadley, probably because he presented to the Royal Society first, and because British naval dominance meant British versions of the instrument became standard. But I think Godfrey deserves equal recognition. His achievement was arguably more impressive, given that he was self-taught and working without institutional support. Regardless of who deserves priority, what matters is that by 1732, the reflecting quadrant, soon to evolve into the sextant, was being tested at sea, and the results were extraordinary. Navigators reported measurements accurate to within 1 or 2 minutes of arc, which translates to about 2 nautical miles of error. Compare that to the astrolabe's 3 to 5 degrees of error, 180 to 300 nautical miles. This wasn't an incremental improvement. This was a revolution. But here's what really blows my mind. The instrument that Hadley, Godfrey, and Leroy invented wasn't actually a sextant yet. It was an octant, which measured angles up to 90 degrees using a 1/8 circle arc. The sextant, measuring angles up to 120 degrees using a 1/6 circle arc, wouldn't be developed until a few years later. But the principle was the same, and the trajectory was set. The astrolabe's reign was over, even if nobody realized it yet. Okay, I need to explain something that's going to sound complicated, but is actually beautifully simple once you understand it. This is the key to why the sextant worked when the astrolabe failed. This is the secret weapon, double reflection. Let me start with a question. How do you measure the angle between two objects, say the sun and the horizon, when you're standing on a platform that's constantly moving and tilting? With an astrolabe, you can't. You need a stable reference point, and on a ship, you don't have one. The genius of the sextant is that it creates its own stable reference point using mirrors and the laws of optics. Here's how it works. I'm going to walk you through this step by step, and I promise it'll make sense. Imagine I'm holding a sextant. It's a roughly triangular frame, traditionally made of brass but sometimes wood, with a curved scale along the bottom edge. On one side of the frame there's a fixed mirror called the horizon glass. This mirror is special. The bottom half is reflective, but the top half is clear glass. On the other arm of the triangle, the pivoting arm called the index arm, there's another mirror called the index mirror. This mirror can rotate as I move the arm along the scale. Now, I also have a small telescope mounted on the frame, aimed at the horizon glass. Here's what happens when I use the sextant to measure the angle between the sun and the horizon. Step 1. I look through the telescope at the horizon glass. Through the clear upper half of the horizon glass, I see the actual horizon directly. Step 2. I adjust the index arm, which pivots the index mirror. Light from the sun hits the index mirror and reflects toward the horizon glass. Step 3. The light bounces off the reflective lower half of the horizon glass and enters my telescope. Step 4. I keep adjusting the index arm until the reflected image of the sun in the lower half of my view lines up perfectly with the direct image of the horizon in the upper half of my view. When they align, I read the angle off the scale. That's my measurement. Now here's the magic, the part that makes this work on a moving ship. Because I'm comparing two images in the same optical field, the direct view of the horizon and the reflected view of the sun, any movement of the ship affects both images equally. If the ship rolls to the left, both the horizon and the sun's reflection move to the left together. The relationship between them stays constant. The measurement stays accurate. This is the principle of double reflection, and it's absolutely brilliant. The light from the celestial body bounces twice, once off the index mirror, once off the horizon glass, before reaching my eye. Because of the laws of reflection, the angle I read on the scale is exactly half the actual angle between the sun and the horizon. The sextant scale accounts for this automatically, showing the true angle. Let me give you an analogy. Imagine you're trying to measure the height of a friend while both of you are on a boat that's rocking up and down. If you use a ruler and try to measure from the ground up, you'll get different measurements every time the boat moves. But what if you could take a picture where both of you are in the frame and measure from the photo? The rocking doesn't matter anymore because you're comparing relative positions in the same reference frame. That's essentially what the sextant does with light and mirrors. The implications of this were staggering. For the first time in human history, navigators could take accurate celestial measurements from a moving ship. They could determine their latitude reliably day or night, in rough seas or calm. The sextant didn't eliminate all navigation errors, but it reduced them by an order of magnitude. But there's another aspect of the sextant's design that I find equally fascinating: its portability and durability. The sextant was much smaller than a mariner's astrolabe. You could hold it in your hands easily, store it in a wooden case, carry it up to the deck when needed. The mirrors were protected within the frame. There were fewer moving parts to corrode or break. And unlike the astrolabe, which required you to look up at the sun or stars, potentially blinding yourself, the sextant used filters and indirect viewing through the telescope. You could measure the sun's altitude at noon, the most important measurement for determining latitude, without damaging your eyes. The sextant also incorporated precision adjustments that weren't possible with the astrolabe. Small tangent screws allowed fine-tuning of the index arm position to fractions of a minute of arc. The scale was divided finely, with a vernier scale that allowed reading to incredible precision. In the hands of a skilled navigator, a good sextant could measure angles to within 10 seconds of arc. That's less than a third of a nautical mile of error. I sometimes wonder what it must have felt like for a navigator in the 1730s or 40s, transitioning from the astrolabe to the sextant. It must have been like switching from a flip phone to a smartphone. Suddenly, you had confidence in your measurements. You could trust your calculations. The ocean became a little less terrifying, a little more knowable. Of course, the sextant wasn't perfect. It couldn't solve every navigation problem. It couldn't determine longitude reliably, for example, which was still the great unsolved challenge of maritime navigation. But what the sextant did, it did brilliantly. It gave navigators a tool that actually worked in the real conditions of ocean sailing. Now I need to address something that might have been bugging you. If Hadley, Godfrey, and Leroy invented the octant in 1731, when did it become a sextant? And why does that matter? The terminology here is actually really interesting because it tells us about how the instrument evolved. Let me break it down. An octant, from the Latin octans, meaning 1/8, used an arc that was 1/8 of a circle, or 45 degrees. Because of the double reflection principle I explained earlier, this 45-degree arc could measure angles up to 90 degrees. That's enough to measure altitude angles from 0 degrees, horizon, to 90 degrees, directly overhead, or zenith. For basic latitude determination, 90 degrees is enough. The sun or stars are never going to appear at an angle greater than 90 degrees above the horizon. So the octant worked perfectly well for the most common navigation tasks. But navigators quickly realized they wanted more. What if you wanted to measure the angle between two stars, neither of which was near the horizon? What if you wanted to measure the angular distance between the moon and a star for longitude calculations? What if you needed more precision and wanted to take multiple measurements and average them? Enter the sextant. A sextant, from sextans meaning 1/6, has an arc of 60 degrees, which can measure angles up to 120 degrees thanks to double reflection. This extra range opened up new possibilities. Navigators could use the lunar distance method for determining longitude, which required measuring precise angles between the moon and specific stars. They could take backsights and perform more sophisticated calculations. They could verify measurements using different celestial bodies. The transition from octant to sextant happened gradually over the 1740s and 1750s. It wasn't that the octant became obsolete. Many sailors continued using octants well into the 19th century because they were cheaper and simpler. But the sextant became the premium choice, the instrument serious navigators aspired to own. And here's something I find really interesting. The names octant and sextant are technically misnomers. The instruments don't actually have 1/8 or 1/6 of a full circle. If you look at a sextant, the arc is usually around 60 to 65 degrees of actual physical arc, not the 60 degrees the name implies. But the name stuck because they describe the functionality, measuring angles up to 90 or 120 degrees, rather than the physical geometry. By the 1760s, the sextant had become standardized in design. The best instrument makers in London, names like Jesse Ramsden, John Bird, and Peter Dolland, were producing exquisite sextants with innovations like achromatic telescopes, which corrected color distortion, adjustable shades for sun observations, and increasingly precise scales. These instruments were expensive. A high-quality sextant in 1770 might cost £15 to £20, equivalent to maybe $8,000 to $10,000 in today's money. For a merchant ship captain or a Navy officer, it was a major investment, but it was worth it. The difference between reaching your destination and being lost at sea? Priceless. I've had the privilege of holding an 18th century sextant in a maritime museum, and I was struck by two things. First, the weight. These instruments were solid brass, heavy in your hands, built to last for decades of hard use at sea. Second, the craftsmanship. Every component precisely machined and fitted, the scale divisions engraved with painstaking accuracy, the mirrors ground and polished to optical perfection. These weren't mass-produced tools. Each sextant was essentially handmade by a skilled craftsman who understood both the theory of optics and the practical needs of navigation. The best sextants were signed by their makers, like works of art. And in a way, they were art, functional art that happened to be one of the most important technologies of the age of exploration. The evolution from octant to sextant also reflects something broader about technological progress. It's not always about radical innovation. Sometimes it's about incremental improvements, extending the range, increasing the precision, refining the design. The octant was revolutionary compared to the astrolabe, but the sextant was the perfected version, the mature form of the technology. And here's the remarkable thing. The basic design of the sextant, established in the mid-1700s, didn't fundamentally change for the next 250 years. Sure, materials improved. Aluminum alloy replaced brass in the 20th century, making sextants lighter. Manufacturing techniques improved, making them more affordable. But if you showed a modern sextant from 1950 to a navigator from 1750, they would recognize it instantly and know exactly how to use it. That's the mark of a truly great design, one that doesn't need to be reinvented, just refined. The sextant found the right answer to the navigation problem, and that answer remained valid for centuries. All right, I need to tell you about one of the most dramatic stories in the history of navigation, a story where the sextant played a crucial supporting role. This is the story of the longitude problem. Let me set the stage. By the mid-1700s, thanks to the sextant determining latitude, your north-south position had become relatively straightforward. At noon, you'd measure the sun's maximum altitude above the horizon with your sextant, do some calculations based on the date and the sun's known position, and boom, you knew your latitude to within a few miles. But longitude, your east-west position, remained maddeningly elusive. And this wasn't just an academic problem. Ships were still getting lost, crashing into rocks, missing their destinations by hundreds of miles. The longitude problem was costing nations fortunes and countless lives. It's why longitude was so hard. Latitude is absolute. It's based on the angle of celestial bodies above the horizon, which changes predictably as you move north or south. But longitude is relative. It's about time. If you know what time it is at your current location and what time it is simultaneously at a reference point, like Greenwich, England, you can calculate your longitude. The Earth rotates 15 degrees per hour, so every hour of time difference equals 15 degrees of longitude. Simple in theory, impossible in practice. Because how do you know what time it is at Greenwich when you're sailing in the middle of the Pacific Ocean? Pendulum clocks existed, but they didn't work on ships. The motion of the waves would stop them or make them wildly inaccurate. Sailors tried using sand glasses, but those weren't precise enough. Some people seriously proposed towing boats full of clocks behind ships or stationing vessels at regular intervals across the ocean as floating time references. Desperate times call for desperate measures, I guess. The British government was so desperate to solve this problem that in 1714 Parliament passed the Longitude Act, offering a prize of £20,000, about $3 million today, to anyone who could devise a practical method for determining longitude at sea to within 30 nautical miles. Two main approaches emerged. The first was the lunar distance method, which is where the sextant comes in. The second was the chronometer, a super-accurate clock that could keep time at sea. Let me explain the lunar distance method because it's absolutely ingenious, and it relied entirely on the sextant's precision. The moon moves relatively quickly across the starry background, completing a full orbit around Earth every month. From Earth, we see the moon appear to pass near different stars on different nights. Astronomers could predict these positions years in advance and publish them in tables called nautical almanacs. Here's the clever part. If I measure the angular distance between the moon and a specific star on a specific night, and I compare my measurement to the predicted distances in the almanac, I can determine the exact time at Greenwich. Then I compare that to my local time, which I determine by observing when stars cross my meridian, and bam, I know my longitude. But this method required incredibly precise angle measurements. We're talking about measuring the angular distance between two celestial bodies to within 1 or 2 minutes of arc. The astrolabe could never have done this. Even early octants struggled. But a high-quality sextant in skilled hands could make these measurements reliably. Throughout the 1750s and 1760s, the lunar distance method was refined by astronomers and navigators like Neville Maskelyne, who became the British Astronomer Royal. Maskelyne was a huge proponent of this method and published detailed nautical almanacs to support it. He also trained naval officers in the complex calculations required. I've looked at these calculations, and they're brutal. Multiple steps of spherical trigonometry, corrections for atmospheric refraction, parallax adjustments. It could take a skilled navigator 30 minutes to an hour to complete all the math for a single longitude determination. But it worked. Ships using the lunar distance method with sextants could determine their longitude to within 30 miles, sometimes better. Meanwhile, a clockmaker named John Harrison was pursuing the chronometer approach. Harrison built a series of increasingly sophisticated marine chronometers, clocks so precisely made that they could keep accurate time even on a pitching, rolling ship with changing temperatures and humidity. His fourth chronometer, H4, completed in 1759, was a masterpiece. It lost less than 5 seconds during a transatlantic voyage. Here's where the story gets interesting. There was a bitter rivalry between the chronometer advocates, led by Harrison, and the lunar distance advocates, led by Maskelyne. Harrison accused Maskelyne of bias because Maskelyne sat on the board of longitude that would award the prize. Maskelyne argued that chronometers were too expensive and too complex for widespread use, while the lunar method just required a sextant and an almanac. In the end, both methods won. Harrison eventually received his prize money after decades of fighting, and chronometers did become the preferred method for longitude determination, once they became affordable. But the lunar distance method remained important for much of the 19th century, especially on ships that couldn't afford a chronometer or needed to verify their chronometer's accuracy, and all of it depended on the sextant. Without the precision of the sextant's double reflection principle, neither method would have been practical. The sextant didn't solve the longitude problem alone, but it was an absolutely essential enabling technology. I sometimes imagine what it must have felt like for Captain James Cook, who used both methods on his famous voyages of exploration in the 1770s. Cook had both Harrison chronometers and sextants for lunar distances. For the first time in human history, he could navigate with real confidence, knowing his position in both latitude and longitude to within a few miles. He could create accurate maps of newly discovered lands. He could sail back to the exact same spots on subsequent voyages. This was revolutionary. The sextant, combined with chronometers and lunar distance tables, transformed the ocean from an unknowable chaos into a measurable, predictable space. It wasn't tamed. The sea is never tamed, but it was comprehensible, and that made all the difference. Okay, it's time for a direct comparison. I want to put the sextant and the astrolabe side by side and really examine what made the difference. Because here's the thing, we remember the sextant as the winner and the astrolabe as the loser, but the reality is more nuanced than that. Let's start with what the astrolabe could do that was actually impressive. The mariner's astrolabe, and I should distinguish here between the mariner's astrolabe and the more complex planispheric astrolabe used by astronomers, was a remarkable piece of technology for its time. It was simple, robust, and didn't require any optics or moving parts beyond a basic pivot. You could drop it on a stone deck, dunk it in seawater, leave it in the sun for years, and it would still work. The astrolabe could measure altitude angles with reasonable accuracy under ideal conditions, standing on solid ground with calm air, taking your time. In those circumstances, a skilled user could get measurements within half a degree, maybe better. That's not terrible. It's enough to determine latitude to within 30 miles or so. The astrolabe was also intuitive to understand. The basic principle, align the alidade with the sun or star, read the angle on the scale, made immediate sense. You didn't need to understand optics or reflection. Training someone to use an astrolabe took days or maybe weeks. And here's something that often gets overlooked. The astrolabe was cheap. You could cast a brass astrolabe relatively easily, engrave the scale, attach an alidade, and you were done. It might cost £1 or £2, a fraction of the cost of a good sextant. For merchant vessels on tight budgets, the astrolabe remained the practical choice well into the 18th century. But now let's talk about the sextant's advantages, because they were overwhelming. First, accuracy. Under practical conditions at sea, a sextant was typically 5 to 10 times more accurate than an astrolabe. We're talking about measurements within 2 minutes of arc versus 10 to 15 minutes of arc. That translates to navigation errors of 2 miles versus 15 to 30 miles. When you're trying to find a small island in the Pacific, that difference is literally life or death. Second, usability in motion. The sextant's double reflection principle meant it worked on a moving ship. The astrolabe was almost unusable in rough seas. I've read accounts of navigators waiting hours or even days for calm enough conditions to take an astrolabe reading. The sextant worked in any weather short of a storm so severe that you couldn't see the horizon. Third, versatility. The sextant could measure angles between any two objects, sun and horizon, star and horizon, moon and star, even two landmarks on shore. The astrolabe was limited to measuring altitude angles. This versatility made the sextant useful for a much wider range of navigation techniques, including the lunar distance method for longitude. Fourth, precision instruments. The sextant incorporated fine adjustment screws, vernier scales, and precision optics that simply didn't exist in astrolabe design. These features allowed measurements to be refined to incredible accuracy. Some late 19th century sextants could measure to within 10 seconds of arc. That's about 300 meters of navigation error. Fifth, eye safety. Measuring the sun with an astrolabe meant either looking at it directly, risking eye damage, or projecting its shadow, less accurate. The sextant used index shades, colored glass filters that protected your eyes while allowing accurate measurement. This seems like a minor point until you consider how many navigators must have damaged their vision using astrolabes over the centuries. But here's what I think is the most important difference, the one that really explains why the sextant triumphed. The sextant was designed specifically for maritime navigation, while the astrolabe was an astronomical instrument adapted for navigation. The astrolabe came from a tradition of land-based astronomy. It was designed for observatories and mountaintops, for careful measurements taken over time, for conditions that don't exist on a ship. When sailors started using it, they were forcing a tool into a role it was never meant to play. The sextant, in contrast, was born from the specific needs of maritime navigation. Hadley, Godfrey, and Leroy were all responding directly to the problem of measuring angles on moving ships. Every design choice in the sextant, the double reflection, the compact frame, the horizon glass, the telescope, was optimized for that specific use case. It's like comparing a sports car to a truck. The sports car is faster and more precise, but the truck has its own advantages in certain contexts. For a long time, the astrolabe was good enough. But as maritime trade expanded, as exploration pushed into more remote waters, as naval warfare became more sophisticated, good enough wasn't good enough anymore. The world needed the precision and reliability of the sextant. There's also a cultural factor that I find fascinating. The astrolabe had centuries of tradition behind it. It was connected to classical learning, to Islamic scholarship, to medieval science. Using an astrolabe wasn't just practical, it was participating in a long intellectual tradition. There was a certain romance to it. The sextant had none of that. It was new, modern, scientific in the Enlightenment sense. It represented a break with tradition, a willingness to question received wisdom and adopt better solutions. The shift from astrolabe to sextant paralleled broader cultural shifts in 18th century Europe, the movement toward empiricism, innovation, and practical problem solving. By the late 1700s, the contest was over. The sextant had won decisively. Naval regulations began mandating sextants. Training curricula shifted. The astrolabe became a historical artifact, something you might see in a museum or a collector's cabinet, but not on the deck of a working ship. And yet, I don't think we should view this as a simple story of progress defeating obsolescence. The astrolabe served humanity well for 2,000 years. It enabled the Islamic Golden Age of astronomy, guided Portuguese explorers around Africa, helped Spanish conquistadors cross the Atlantic. It was a magnificent achievement of human ingenuity. The sextant didn't make the astrolabe wrong, it just made it unnecessary. And that's an important distinction. Now I want to take you on a journey through what I call the Golden Age of sextant navigation. Roughly 1750 to 1950, 200 years during which this instrument became the most important tool in humanity's effort to map and understand our planet. Let me start with Captain James Cook, because his story perfectly illustrates the transformative power of the sextant. When Cook set sail on his first voyage aboard HMS Endeavour in 1768, he carried with him the latest navigation technology, precision sextants, and a chronometer copy of Harrison's design. His mission was ostensibly to observe the transit of Venus from Tahiti, but his secret orders were to search for the mysterious southern continent that many geographers believed must exist. Over 3 voyages, spanning 12 years, Cook mapped more of the Earth's surface than any human being before him. He charted the coast of New Zealand, proving it was 2 islands, not one. He mapped the eastern coast of Australia. He ventured farther south than anyone had ever gone, crossing the Antarctic Circle multiple times. He accurately mapped countless Pacific islands, many of which had never been precisely located before. And he did all of this because he could trust his navigation. With his sextant, Cook could determine his position with unprecedented accuracy. He could return to the exact same anchorage on a subsequent voyage. He could create maps that other navigators could actually use. His charts of New Zealand and the Pacific were so accurate that they remained in use well into the 20th century. I've seen some of Cook's original charts, and what strikes me is the confidence in the lines. Earlier maps were tentative, vague, often wildly inaccurate. Cook's maps are precise, detailed, authoritative. That's the difference the sextant made. After Cook, the floodgates opened. The late 18th and early 19th centuries saw an explosion of maritime exploration. French expeditions under La Pérouse and d'Entrecasteaux explored the Pacific. British expeditions under Vancouver charted the Pacific Northwest of North America. Russian expeditions under Bellingshausen circumnavigated Antarctica. Spanish expeditions mapped the Philippines and the Western Americas. All of them relied on sextants, but it wasn't just government-sponsored exploration. Commercial shipping expanded dramatically because captains could navigate more confidently. The China trade, the whaling industry, the shipping routes to Australia and South America, all of these became safer and more profitable because of sextant navigation. Let me give you a specific example of how important this was. The clipper ship era of the mid-1800s saw sailing vessels racing from New York or Boston around Cape Horn to San Francisco, carrying cargo and passengers to the California goldfields. These voyages took 3 to 4 months and covered over 15,000 miles. The fastest ships, like the famous Flying Cloud, could make the journey in under 90 days. This was only possible because navigators could plot optimal routes using sextant observations. They could take advantage of favorable winds and currents, avoid dangerous areas, make precise landfall at their destination. The clipper ships weren't just fast because of their design. They were fast because their captains could navigate with precision. The sextant also played a crucial role in scientific oceanography. In 1872, HMS Challenger embarked on the first major scientific expedition focused on studying the oceans themselves rather than just getting from point A to point B. Over 4 years, the Challenger expedition traveled nearly 70,000 nautical miles, taking depth soundings, collecting water samples, cataloging marine life, and mapping ocean currents and temperatures. Every single one of those 70,000 miles was navigated using sextants. The scientists needed to know exactly where each sample was collected, where each depth sounding was taken. The sextant made that precision possible, and the Challenger expedition laid the foundations for modern oceanography. I'm also fascinated by how the sextant enabled polar exploration. The expeditions to the Arctic and Antarctic in the late 19th and early 20th centuries, Shackleton, Scott, Amundsen, Peary, all depended on sextant navigation in some of the most challenging conditions imaginable. Imagine trying to take a sextant reading when it's 40 degrees below zero, you're wearing thick gloves, your fingers are numb, and the sun is barely above the horizon. Or trying to navigate when the ice is constantly drifting, when magnetic compasses become unreliable near the poles, when there are no landmarks and everything looks the same. Yet explorers did it, relying on their sextants to guide them across the polar ice. Roald Amundsen's successful expedition to the South Pole in 1911 used regular sextant observations to verify their position as they traveled across the featureless Antarctic ice sheet. When they reached the pole, Amundsen took multiple sextant readings over 24 hours to confirm they were actually at 90 degrees south latitude. Without the sextant, they would have had no way to know if they'd achieved their goal. But here's what really amazes me. The sextant wasn't just for professionals. By the mid-1800s, sextants had become affordable enough that amateur sailors, explorers, and adventurers could own them. Navigation manuals taught the principles of celestial navigation to anyone willing to learn. The ocean became accessible to people who weren't naval officers or professional merchant captains. This democratization of navigation enabled all sorts of remarkable journeys. Joshua Slocum, a Massachusetts sea captain, became the first person to sail single-handed around the world from 1895 to 1898. He navigated the entire 36,000-mile voyage using a basic sextant and a tin clock. His book, Sailing Alone Around the World, inspired generations of sailors and adventurers. By the early 20th century, the sextant had become so central to maritime culture that it was iconic. It appeared in naval emblems, maritime art, and literature. To be a navigator was to be a person who could read the stars with a sextant. It represented mastery over nature, scientific knowledge applied to practical ends, the human ability to venture into the unknown and find the way back. The sextant's golden age also coincided with World War I and World War II, when maritime navigation became a matter of survival. Warships needed to know their positions precisely for gunnery calculations and fleet maneuvers. Submarines navigated using periscope sextants when surfaced. Transport ships carrying troops and supplies across the Atlantic depended on accurate navigation to avoid U-boats and reach their destinations. During World War II, the United States Navy trained over 100,000 officers in celestial navigation using sextants. There were massive programs to manufacture sextants. They went from handcrafted instruments made by a few specialized firms to mass-produced tools made by the thousands. The quality didn't decline. If anything, manufacturing precision improved with modern techniques. I've read accounts from World War II navigators describing the almost meditative quality of taking star sights at dawn or dusk when both the horizon and the stars were visible. Even in the midst of war, there was something peaceful about standing on deck with a sextant, connecting with the ancient practice of reading the heavens for direction. By 1950, at the end of our golden age, the sextant had become the most refined version of itself. Lightweight aluminum alloys had replaced heavy brass. Precision optics gave crystal-clear views. Manufacturing tolerances were measured in seconds of arc. The sextant of 1950 was recognizably the same instrument as Hadley's quadrant of 1731, but perfected through 2 centuries of incremental improvements. And then something changed. Something that would eventually make the sextant itself obsolete, just as the sextant had made the astrolabe obsolete. But before we get to that, there's one more crucial topic I need to address. Here's a question I get asked a lot. Why, in the age of GPS satellites and digital navigation, does anyone still use a sextant? It's 2025. I can open my phone and know my position anywhere on Earth to within a few feet. Modern ships have multiple GPS receivers, radar, electronic charts, and automated navigation systems. So why would anyone bother learning celestial navigation with a sextant? The answer is both practical and profound, and it tells us something important about technology and resilience. Let me start with the military perspective. The United States Naval Academy still requires midshipmen to learn celestial navigation using sextants. Navy SEALs train with sextants as part of their survival skills. Nuclear submarines, despite having the most sophisticated navigation systems in the world, still carry sextants and train navigators to use them. Why? Because GPS can fail. GPS satellites can be jammed or spoofed. That is, someone can broadcast false signals that give you the wrong position. GPS signals are actually quite weak by the time they reach Earth's surface, and it doesn't take much power to overwhelm them. In a military conflict, adversaries might deliberately take down GPS satellites or interfere with signals. There have been numerous reported incidents of GPS jamming in conflict zones like Syria, Ukraine, and the South China Sea. Solar storms can also disrupt GPS and other satellite systems. A major geomagnetic storm, like the Carrington event of 1859, could potentially knock out many satellites and electrical systems. If that happened today, GPS would be gone, potentially for months or years. And here's the thing, a sextant doesn't depend on anything except the sun, moon, stars, and your knowledge of how to use it. It can't be jammed, it can't be hacked. It doesn't need electricity or satellites or ground stations. As long as you can see the sky and the horizon, you can navigate. This is why maritime safety regulations still recommend that ships carry sextants as backup navigation equipment. It's also why serious blue water sailors, people who cross oceans in small boats, learn celestial navigation even though they have GPS. Because if you're 1,000 miles from land and your electronics fail, you need a way to know where you are and how to reach safety. I've talked to modern sailors who practice celestial navigation as a regular discipline, taking star sights even though they have GPS, just to maintain their skills. They describe it as a kind of insurance policy, but also as something deeper, a connection to maritime tradition, a self-reliance that electronic navigation can't provide. There's also an educational argument for learning sextant navigation. Understanding celestial navigation requires understanding spherical geometry, the motions of celestial bodies, coordinate systems, and time zones. It requires careful observation and precise calculation. These are valuable cognitive skills that have applications beyond navigation. The United States Merchant Marine Academy, Coast Guard Academy, and various maritime colleges worldwide still teach celestial navigation, not just for backup purposes, but because it makes better navigators. Someone who understands how to navigate by the stars has a deeper comprehension of where they are on the planet and how navigation works. When their GPS tells them their position, they can sanity check it against their understanding of where they should be. But there's also something philosophical about the sextant's continued relevance. In an age where we're increasingly dependent on complex, fragile technological systems, there's value in preserving simple, robust alternatives. The sextant represents a kind of technological sustainability, a tool that works without infrastructure, without supply chains, without any system beyond itself. Let me give you a contemporary example. In 2017, the USS Fitzgerald and USS John S. McCain, both guided missile destroyers, were involved in separate collisions with merchant vessels. Multiple crew members died. Investigations revealed that over-reliance on electronic navigation systems and inadequate training in basic navigation principles contributed to both accidents. Following these disasters, the United States Navy significantly increased its emphasis on basic seamanship and celestial navigation training. The reasoning was simple. Navigators who understand fundamental principles are less likely to blindly trust faulty electronic readouts. The Sextant, as a teaching tool, helps develop that fundamental understanding. I've also discovered a small but dedicated community of amateur astronomers and navigators who practice celestial navigation as a hobby. There are online forums, published tables for celestial navigation, even smartphone apps that help with the calculations while you still use a physical sextant for measurements. These enthusiasts keep the knowledge alive and continue to refine teaching methods for new generations. Some sailing schools have reported increased interest in celestial navigation courses in recent years. Part of this is romantic. People want to learn the traditional skills of old-time sailors. Part of it is practical. Sailors want backup skills in case of electronic failure. And part of it seems to be a broader cultural interest in self-sufficiency and traditional crafts. I find it beautiful that in 2025 you can still buy a new sextant. Companies like Astra 3B Tamaya and Celestaire manufacture modern sextants using contemporary materials and precision manufacturing, but following designs that would be recognizable to a navigator from 1850. These aren't antiques or museum pieces. They're working tools that people actually use. There's also something poetic about the continuity. Somewhere in the world right now, someone is taking a sun sight with a sextant, using the same principles that Hadley discovered in 1731, measuring their position using the same stars that guided Cook, Magellan, and countless anonymous sailors throughout history. That unbroken chain of knowledge and practice, spanning 3 centuries, is remarkable. The sextant has outlived the technology that was supposed to replace it. Radio direction finding, LORAN-C, early satellite navigation systems. GPS is more convenient, but the sextant is more resilient. And in a world of increasing technological complexity and fragility, resilience matters. I'm not suggesting we abandon GPS. That would be absurd. GPS is an incredible achievement that makes navigation safer, easier, and more precise than ever before. But I am suggesting that preserving the knowledge of celestial navigation with sextants is valuable. It's a backup system, an educational tool, a connection to our past, and a reminder that the best technologies are sometimes the simplest ones. So yes, Navy SEALs still train with 300-year-old tools, and honestly, that makes perfect sense to me. We've come to the end of our journey through the fascinating story of the sextant, from the astrolabe's failures to 3 simultaneous inventors, from the physics of double reflection to mapping the unknown world, from solving the longitude problem to surviving in the modern age. But here's the thing about exploration, it never really ends. Every answer opens up new questions. Every discovery reveals new mysteries. Throughout this video, I've touched on so many topics that could be their own deep dives. The chronometer and John Harrison's 40-year battle to claim his prize, the lunar distance method and the complex mathematics of spherical trigonometry, the clipper ships and the race to set speed records around the world, the polar expeditions and the challenges of navigation in the extreme latitudes, the development of GPS and how satellite navigation actually works. And beyond navigation, there are countless other stories of instruments and technologies that changed the world. The telescope that revealed the cosmos, the microscope that discovered the invisible world of cells and microbes, the compass that first allowed reliable long-distance travel, the printing press that democratized knowledge, the telegraph that shrank distances, the transistor that launched the digital age. Each of these has a story as rich and fascinating as the sextants. Each represents a moment when human ingenuity found a solution to a seemingly impossible problem. Each changed not just what we could do, but how we understood ourselves and our place in the universe. So here's what I want from you. I want you to be part of this journey of discovery. First, if you've enjoyed this deep dive into the history of navigation and technology, I need you to subscribe to this channel and hit that notification bell. We're building a community of people who are genuinely curious about how the world works, who appreciate the stories behind the tools and technologies we often take for granted. By subscribing, you're joining that community and helping us create more content like this. Second, smash that like button. I know, every YouTuber says this, but it actually matters. The algorithm looks at engagement to decide whether to recommend videos to new viewers. Your like helps other curious people discover these stories. It helps the channel grow, which allows us to invest more time and resources into research and production. So if you found value in this video, that like button is how you can directly support more content like this. Third, and this is the most important one, I want you to comment. Tell me what you thought of the sextant story. Tell me if you've ever used a sextant or learned celestial navigation. Tell me if this changed how you think about maritime history or technology or exploration. But more than that, I want your suggestions. What navigation mystery should we uncover next? What technology's origin story do you want to hear? What historical puzzle keeps you up at night wondering about the answer? Are you curious about how the compass was invented and how it revolutionized travel? Do you want to know the true story of GPS and the satellites that guide us every day? Should we explore the history of maps and how humans learned to represent their world on paper? Are you interested in the development of radar and sonar during World War II? Or should we go in a completely different direction? The history of timekeeping, the invention of the telescope, the development of submarines. Leave your suggestions in the comments. I read every single one, and your input directly influences what videos we create next. This channel isn't just me talking at you. It's a conversation, a collaborative exploration of the amazing stories hidden in the tools and technologies around us. I also want to hear your personal stories. Have you ever been lost at sea? Have you navigated using traditional methods? Do you have family members who were navigators in the Navy or Merchant Marine? Do you collect historical instruments? Have you visited maritime museums with impressive collections of sextants and other navigation tools? Share those stories in the comments. Let's learn from each other's experiences. And if you're a teacher or educator, tell me how you might use this content in your classroom. I'd love to know how these stories can help inspire the next generation of explorers, scientists, and engineers. One more thing. If you want to go deeper into any of the topics we've covered, I've included links in the description to books, articles, museums, and resources where you can continue your exploration. The story of the sextant intersects with astronomy, physics, mathematics, history, engineering, and even art. There's so much more to discover. I've spent months researching this video, reading historical accounts, examining original instruments in museums, talking to modern navigators and historians. But I'm not an expert on everything, and I may have gotten some details wrong or missed important aspects of the story. If you catch an error or have additional information, please let me know in the comments. This is how we all learn together. Before I sign off, I want to leave you with one final thought. The sextant's story is ultimately a story about human ingenuity and adaptability. For 2,000 years we used the astrolabe, and it worked well enough. But when our needs changed, when we pushed into new frontiers, when good enough wasn't good enough anymore, we didn't just accept the limitations of our tools, we invented better ones. Hadley, Godfrey, and Leroy didn't set out to create a historical milestone. They were just trying to solve a practical problem that was costing lives and money. But their solution became one of the most important instruments in human history, enabling 2 centuries of exploration, trade, scientific discovery, and adventure. That's the power of innovation driven by real needs. That's what happens when creative minds focus on practical problems. And that's a lesson that's just as relevant today as it was in 1731. We live in an age of unprecedented technological capability, but we also face unprecedented challenges. Climate change, disease, resource scarcity, the need for sustainable energy, the exploration of space. These are the navigation problems of our time. And somewhere right now, there are people working on the solutions that will seem as revolutionary to future generations as the Sextant seemed to 18th century sailors. Maybe one of those people is you. Maybe something in this video sparked an idea, or reminded you why you're fascinated by science and technology, or inspired you to dig deeper into a historical mystery that could inform future innovations. That's why I make these videos. Not just to tell interesting stories about old instruments, but to celebrate human creativity and problem-solving. To remind us that the tools we use today were once impossible dreams. To show that knowledge builds on knowledge, that today's innovations stand on the shoulders of yesterday's breakthroughs. The Sextant surpassed the Astrolabe, GPS surpassed the Sextant. But the Sextant survives because it solved its problems so elegantly, so completely, that it remains relevant even in an age of satellites and computers. That's the mark of truly great design. So what will you create that lasts 300 years? What problem will you solve that changes the world? What story will future generations tell about your contribution to human knowledge and capability? I don't know the answers to those questions, but I do know this. Every great achievement starts with curiosity, with asking questions, with wanting to understand how things work and why they matter. The Sextant taught us that sometimes the solution to our greatest challenges comes from looking at old problems in new ways. The Astrolabe wasn't wrong. It was just designed for a different context. The Sextant didn't destroy its predecessor out of malice. It simply answered a question more effectively. How do we navigate accurately on a moving ship in the middle of an ocean? And here's the beautiful irony that I want you to carry with you. The Sextant, which made the Astrolabe obsolete, now faces its own obsolescence with GPS. But just as the Astrolabe had value beyond pure navigation, as a teaching tool, as a connection to history, as a symbol of human ingenuity, the Sextant retains its value even in our satellite age. I keep a small antique sextant on my desk. It's from the late 1800s, made of brass that's turned green with age. The mirrors are slightly cloudy, and the scale shows wear from a century of use. I don't use it for navigation. I wouldn't even know whose hands held it aboard what forgotten ship on what distant voyage, but I keep it there as a reminder that every impossible problem has a solution waiting to be discovered. That sometimes 3 people on different sides of the world can arrive at the same answer because the truth has a way of revealing itself to those who search diligently. That the tools we create to master our world also shape how we understand ourselves. That knowledge, once gained, is never truly lost. It transforms and adapts and finds new relevance in unexpected ways. When I pick up that old sextant and look through its telescope, even here in my landlocked office, I'm connected to Captain Cook charting the Pacific, to Admiral Shovel sailing to his doom before this technology existed, to John Hadley hunched over his workbench, perfecting his mirrors, to Thomas Godfrey explaining his invention to skeptical sea captains, to millions of anonymous sailors who trusted this instrument to bring them home safely. That's the real mystery of the Sextant. Not how it works, we've covered that. not why it succeeded. We understand that too. The real mystery is how a simple arrangement of mirrors and brass can connect us across centuries, can carry the accumulated wisdom of generations, can remain relevant through revolutionary changes in technology. The astrolabe served humanity for 2,000 years. The sextant has served us for 300 years and counting. GPS has only been fully operational since 1995, just 30 years. What will replace GPS? What will come after that? I don't know. But I do know that whatever innovations lie ahead, they'll build on everything that came before. They'll carry forward the same fundamental human drive to know where we are, to find our way home, to navigate safely through unknown waters. And maybe, just maybe, 300 years from now, someone will make a video about GPS, about how this constellation of satellites revolutionized navigation, how it dominated for centuries, and how it was eventually superseded by something we can't even imagine yet. And they'll wonder why, despite having even more advanced technology, people still learn to use GPS as a backup skill, as a connection to history, as a way of understanding the fundamentals of how navigation works. Because that's what the sextant teaches us in the end. The best tools don't just solve problems, they teach us how to think about problems. They connect us to the people who struggled with those problems before us. They remind us that we're part of a long story of human curiosity and ingenuity. So yes, the sextant surpassed the astrolabe. GPS surpassed the sextant. But the story doesn't end with obsolescence. It ends with transformation, with tools finding new purposes, with knowledge being preserved and passed forward, with each generation building on the achievements of the last while preparing the foundation for the next. That's not just the story of navigation instruments. That's the story of human progress itself. Thank you for joining me on this journey through the mystery of the sextant. Thank you for your curiosity, your time, and your attention. I hope this video has given you a new appreciation for the seemingly simple instruments that changed history. And maybe, just maybe, inspired you to think differently about the tools you use every day and the innovations still waiting to be discovered. Now it's your turn. Subscribe so you don't miss our next exploration into the fascinating intersections of science, history, and technology. Hit that like button if this story resonated with you. And most importantly, drop a comment telling me what navigation mystery, what technological evolution, what historical innovation you want us to uncover next. Your engagement doesn't just help the channel. It helps build a community of curious minds who understand that every tool has a story, every innovation has a history, and every solved mystery opens the door to new questions worth asking. Until next time, keep looking up at the stars, keep asking questions, keep challenging what you think you know, and keep exploring this amazing world of ours. Whether you're navigating by satellite or by sextant, by astrolabe or by instinct, the important thing is that you keep moving forward, keep discovering, keep pushing the boundaries of what's possible. The ocean of knowledge is vast and deep, but with curiosity as your compass and determination as your sextant, there's no horizon you can't reach. I'll see you in the next video. Safe travels, fellow explorers.